Cosmos, Data, Entity Framework, Power Tools,
Netology Suite.
Countdown commencing. T-2 minutes.
Jeremy Lickness,
Shiro Dance,
Grace Lampson,
Martha Vickers.
.NET Data. T-1 minute. Thirty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff. We are go for .NET Data Community Standup.
Okay, here we are again. .NET Data Community Standup. This week we're going to talk about hierarchical data. So I'm joined by Shai from the .NET Data Access team as always, and then also Bryce, who has worked with the community on this over the years. So he's going to talk in a little bit about the kind of community history of this. As is always the case, it's been a little bit of a scramble getting everything ready. So if there's some live demo issues, then that's the way it goes. But we'll see what happens. Okay, so let's start as always with the state of the unicorn. Seems like forever ago that we released these things now, but it's actually less than 2 weeks. So 704 is out there. It's 7 more bug fixes. We got a lot of bug fixes in 703, but there's still, important stuff still coming in. So get 704. Actually, one of those bug fixes is in Microsoft Data SQL Client, not in EF, and we always forget about it. We never mention Microsoft Data SQL Client, and it's Bryce's thing that he created and everything. So sorry, Bryce, that we always just gloss over that. But yeah, there's a bug fix in Microsoft Data SQL Client. I guess it's good that there's hardly ever any bug fixes in it, right? But there is one in this case. So. Okay, and then also EF Core 8 Preview 2 is on NuGet, which has SQL Server Hierarchy ID official support, which we're going to talk about today, and then also JSON columns in SQLite. So this is the same support we had for JSON columns in SQL Server, now works on SQLite as well. We're still working on lots of improvements in the SQLite space. Maurice is working hard on that, but what you could do in SQL Server, you can now do in SQLite. Plus, of course, there's already been some enhancements to JSON column support in Preview 1, and those also work on SQLite. As always, aka MS EF8-new. That's the what's new in EF8, and there's runnable samples on GitHub. I will try and upload the code that I'm doing here to GitHub later. I haven't done it yet because it's a bit of a scramble, but also the code from the stand-up I'll put there. Okay, So let's talk a little bit about hierarchical data, what we mean by that, which is, and we'll get into this a little bit more later when we look at differences between Postgres and SQL Server as well. But for now, we're just going to kind of do the kind of common denominator type thing. So we've got a very famous family tree here of hobbits. I've been trying to avoid saying trademark terms in writing them down in any of the online stuff. So we refer to them as halflings in anything that's written down. And
I don't think hobbits are like a
oh, it's
trademark
trademark.
thing.
Tolkien estate. Yes.
Are you saying he invented hobbits? I'm very
Yes.
surprised. Isn't this
Yes.
like an English word from the whatever? Like
Oh, well, we could go into the language history of it.
we
maybe,
absolutely
but-
should. No, I'm kidding.
Anyway, if they had to cease and desist and tell us to remove this YouTube video, then we will do that. But, you know, I figured I can be a little bit more free on the video than I have been on stuff we publish on the .NET vlog or whatever. Anyway, so what do we mean by hierarchical data? Essentially tree structures. I mean, that's basically what it means. You've got a root and then you've got nodes down in the tree going to leaves. So that's essentially what we mean by hierarchical data. SQL Server has a particular syntax for representing these things. Postgres syntax is more flexible. But what I'm going to do is, just to make this really clear, I'm going to go through this tree structure and show the SQL Server syntax so that when we get to looking at the code, you can kind of mentally move back between the kind of tree image and what you're seeing, you know, in terms of what's in the code. So in SQL Server, the root is just a slash. That's the patriarch of the family. Of course, this Tolkien's days, you know, this is a patriarchal family tree. You know, that's just the way it is. Sorry, but that's what's in the book, so that's what we're using. Anyway, okay, so now we get to the first level. So on SQL Server, the first level, each level is basically prepends the level before it. So the root is slash, and then the first level is /1, /2, /3, /4, /5. So all these are all the children on the first level. Okay. Now, when we go down to the children of Mungo, again, these are all prefixed. All the children of Mungo are prefixed by Mungo's hierarchy ID. This is what this is. This is the hierarchy ID. So you know, the first child is Mungo's prefix /1, and then 2, 3, 4, 5. And likewise, if we go to Ponto here, since Ponto was 3, then Rosa is 3.1, and Polo is 3.2, and so on for other ones. And then likewise, when we go down to the next level, it's just the same thing, the prefix, and then you add another suffix on the end of it. And so Bilbo 111. So you can tell why Bilbo inherited Bag End, because Bilbo is the first line male descendant in the Baggins family tree there. Okay. Otho, somewhat infamous, and Falco, 151, and then Posco and Priska. I assume that's how you say that. And then, of course, now we're going down this other side of the family tree where everything is from Largo. So these are all prefixed with 4. And when we get down to here, we've got 4, 1, 2, and so on. Okay, and then final Lotho, very, very infamous Sackville Badmins there. Poppy, Ponto, Porto, and Peony, and then Frodo, as I think most people have heard of Frodo. So 4121. So this, and then I think we've got 2 more in here, yeah. And then Angelica's the only 5th level one we have right now. So this is basically what we mean by a tree structure, a hierarchy. Now, like I said, Postgres, there's a bit more flexibility in this, but let's stick with the SQL Server kind of convention just to start with. Okay, so I'm gonna switch to show some code. I've got a lot of code here, and we're going to look at, and I've got both SQL Server and Postgres examples in here. So we're going to look at both how you do this in Postgres and SQL Server. Before we go into that, let's talk a little bit about the packages involved, the history of how this came about, and this is for SQL Server specifically. The hierarchy ID has actually been supported for quite some time, and let me find my window here. So it's been supported quite some time by this community project. You want to talk about how that came about, Bryce, and the history of this?
Yeah, sure. So way back in EF Core 2.2, which was released in like this November 2019 or somewhere around there. Is that right? That might be right. Anyway, whenever that was, I was doing a bunch of the spatial work, which was bringing in the SQL geometry and the SQL geography types. And while I was doing that work, I'm like, we could easily do this the exact same for hierarchy ID. But the problem was there wasn't like a hierarchy ID library out there. So with spatial, we chose a topology suite. But for the hierarchy ID, I found a community package by Morten Nilsson, who actually brought in a bunch of the spatial stuff. It was unsupported though, so we were hesitant to like just say, hey, yeah, let's merge unsupported code into the main entity framework core branch. So I spiked down some code. I wrote down some code and I put it out there. I don't even know if it was working completely. And then I, of course, got distracted with other features. But a community member named Adam Jones wanted hierarchy ID support. So he found it and he brought it up to speed and he got it like working end to end with tests. And so we released it. And I think we even released it compatible with Entity Framework Core 2.2. And then we've kept stringing it along. There's been lots of contributions to it to evolve it, to add this functionality. But it wasn't until earlier this year, that the SQL Server team finally released official SQL hierarchy ID support. And so what we did is we reached out to all the community members who had contributed and said, hey, would you guys want to contribute all of this into the main Entity Framework Core project so it can become official and supported now that we can like have end-to-end support? And so they all happily agreed. Obviously, they wanted hierarchy ID support in Entity Framework Core. That's why they contributed.
Yeah.
And so, yeah, we just recently in time for 8.0 preview 2, I actually merged all the code in. So that's how it's finally an official package. But the package has been around for a while, so it's been pretty heavily tested by the community. It has some rough edges, but the functionality is pretty well.
Yeah. So thanks to everybody who's in the community who's contributed over this. Like you made this happen, so we really appreciate it. And also, if you're watching this and you're like, I'm not on EF8 yet, remember there is a community package here, so you can do this. I mean, I don't even know how far it goes back. At least 3.1, which isn't even supported anymore. So basically, whatever version of supported EF Core you're using, because obviously you're not using an unsupported version, right? So every version of EF Core that you're using has some form of hierarchy ID support, which is basically this, maybe a few differences, but basically the same as what we're going to show here. Basically the same code. Okay, so let's talk also a little bit about packages for hierarchy ID. So there's kind of 3 levels of packages and assemblies, and this is usually not that important. Usually what you want to do is just include this in your project. The Microsoft Entity Framework Core SQL Server Hierarchy ID project package. And that brings in everything you need to write queries, to integrate with EF Core and all of that stuff, okay? But actually this package itself is dependent on this package called SQL Server Abstractions, which is another new package. This has the actual hierarchy ID type that you can put in your entities in it that you'll see in a minute. And this is like all of our abstractions package. This is a very light dependencies. See, it doesn't depend critically on any other entity framework packages. So if you're trying to keep your data access code, if you like, out of your model, but you want to use hierarchy IDs in your model, then you bring this in and you get very minimal dependencies, so very minimal impact on your deployment. And then, as Bryce mentioned, at the lowest level, this is the Microsoft SQL Server Types package. This is the one that the SQL Server people have released to actually support various custom UDTs essentially that were in SQL Server. So this is the spatial types, geometry and geography, and the hierarchy ID type. And then I don't know if are there any others, Bryce? No, those
No,
are
I
the
think
only
that's all
ones.
there are.
Yeah. So this is kind of the lowest level thing, and this is tied. These things are SQL Server dependent. As we'll see in a minute, the Postgres stuff is independent of this. It would have been nice if we had some kind of common thing between them, but there's quite a lot of differences. And as Bryce says, there wasn't a community library, and so we've ended up here. So it's not, a lot of the functionality is very similar, but the actual types that you use are different.
It's
Okay.
worth pointing out too that the hierarchy ID type is backed by the SQL Server types library,
Yes.
and that will work outside of SQL Server. So if you're just in a pure .NET app,
Absolutely,
you can use
yes.
these, and all the functionality will work. So.
Yes. Yeah, it's a little bit different from geometry and geography in that all of the methods have client implementations, right, Bryce, in the hierarchy ID, so that even though, like in SQL Server right now, if you use one of the geography from this and then you do something, it's not implemented everywhere on the client side. It only works in a translation, whereas hierarchy ID is a lot simpler.
It actually works on Windows, and
On
the reason
Windows,
because of that is because there's a native DLL. It's highly optimized code. Like they want spatial operations to be fast.
But hierarchy ID is not like that. It will work everywhere.
Pure managed, it's all running managed code.
Okay, so let's go back to the code then. Is it? And should we stop for any questions, Shai? I haven't been looking at the chat.
I don't think. I think let's go see some hierarchy ID, and then there's already some questions, but better deal with them after we see some code.
Okay. So in order to get hierarchy ID support in with SQL Server, you need to do this use hierarchy ID thing. That tells us, that tells us to map the hierarchy ID type and everything like that. If you're doing Postgres, you don't need to do that because Postgres has the ltree type, which is equivalent to hierarchy ID built into the ADO.NET provider. It brings it in anyway, and so it's all there by default. I'm using user secrets so that Shai can't see my Postgres password there. Anyway, that's neither here nor there.
Nice.
Okay, so let's look at the little application I have here to test things out, make a clean database, and then seed it with some hierarchy ID things. So if we go back and remember this here, so we had all of these, we built up these hierarchy ID strings. So this is what I'm now adding to the SQL Server database. So I have a class called Hobbit that has a name, year of birth, and then in here I've got the hierarchy ID, which is the path down from the patriarch to this particular item in the tree. I could make this the primary key. That's valid. You can use hierarchy IDs as the primary key. You can't mutate it. EF doesn't allow you to mutate if it's the primary key in. So if you want to reparent part of the tree to another part, then it's kind of nice not having it as the primary key. But anyway, that's an option that there is there. Now, actually, SQL Server has this compact performant binary representation of hierarchy IDs under the hood. And so what we're doing here was we're saying pass from this human readable string format and to create that representation. I think in the API review, we said we're going to make a public constructor for this rather than necessarily having to call pass. Really, you don't need to worry generally about the fact that the binary representation is there. Just think about it in terms of the strings and everything's fine. But under the covers, it's not actually storing a string in SQL Server. It's storing a compact binary representation of that thing. Does Postgres have that too, Shai? Do you know?
I have no idea. I mean, it's a purely internal implementation detail inside Postgres. So who knows?
Okay. Anyway, so yeah, we're doing a normal thing here where I've added all these things and I'm calling save changes. Let's look at the Postgres version of this. Now, the Postgres version of this doesn't have the same strict syntax that SQL Server does. In fact, all it requires is that you have a dot, period, character separating each level. So you can put alphanumeric characters in there. You can do various other things, and we'll come back to that a bit later. I have another example down here that uses that and shows a bit more of that later. But for now, just to keep things very common between what we're doing on SQL Server and Postgres so we can see the same kinds of operations, all I've done is take the same kind of SQL Server representation and put periods in it here. This can cause some issues if you're not very careful with Postgres, because you don't have a lot of uniqueness like this. If you're looking at subtrees, for example, the 1.1 exists lots of different places in here and has different meanings, but we'll get back to that later. But just be aware that you might not want to make it this simple in Postgres depending on your case. We can come back and look at that. Okay, so we've stored data. Let's do something interesting. Let's do some queries. Okay, so I've got all the queries here because I was, rather than copying and pasting them in from elsewhere, I was getting very confused about which were my Postgres ones and which were my SQL Server ones. So I'm just going to uncomment them as we go so I don't get confused. Find a generations. Well, there's a typo. Find a generation. One of the first things that you can do, whether or not this is common, Shai might say that this is a bit artificial. I think it depends on how you're conceptualizing the family tree, but you can say give me everything at a certain level. So on here, so if we say this is level 0, this is level 1 and level 2, so we're saying give all of these at this level, no matter what their ancestors are. If they're at this level in the tree, give me them all. And in order to do that, the hierarchy ID type has this get level function, and you can match that to a level. So if we run this, you'll see, oh, I'm running the Postgres one. I knew that was going to happen. Maybe I'll just do it in here. Okay, run SQL Server. There we go. Okay, so we're going to store all the data. Actually, before we look at the output of the query, let's just take a quick look at the tables just so we can see the hierarchy ID in the table. So here you can see that we've created a table and we're using this SQL Server type hierarchy ID. So this is a built-in UDT, if that's not a contradiction in terms in SQL Server. Okay, so now when we run this query, you can see we get this translated, and it's translated to the where clause where it's using the get level on the UDT in SQL Server, and as you can see, we're returning all of those hobbits that are at that generation 2. Okay, so in Postgres, okay, so in Postgres, let me delete all this white space, and we've got exactly the same thing. The difference is that in Postgres it's a property called nLevel instead of a method called getLevel. But if we run it, oh, and also I think I might not have mentioned this. In Postgres, the actual type is not called hierarchy ID, it's called ltree, but it means basically the same thing.
ltree stands for label tree, like a tree of labels. That's the, but yeah, we'll talk about that a bit later, I think.
Yeah. Okay. So running this, I won't show the table. It's the same as it was in SQL Server, just with ltree as the type. But you can see we get essentially the same thing, except we've translated to this nLevel Postgres function. And then we get the same results out of here. So pretty simple, but translated to the server, presumably done efficiently on the server. That's what the idea of storing these things in this way is, that you do it efficiently on the server. Okay, so we'll stay on Postgres since we're here right now. We can, of course, and the example I've done this and did for this in the What's New docs, I realized afterwards was much more complicated than it needs to be. We want to find all generations, so I'm doing a group by here. So just group by the level. And if we run that, we should see that we get all 11, or a group for each level. Okay, there we go. So we've got each level in a tree, which is exactly this level, this level, this level, this level, down to Angelica by herself at the end there. Just a little digression here. This is group by as a final operator. You might notice there's no grouping in SQL. Shy?
Am I
anything
supposed to
about that?
comment? So this is something, this query, if you tried this before EF Core 7, this would result in an error. Now, we would not translate this. And the reason is, previously, we would only do group by when we could translate it to a SQL Server group by. And in SQL, or to SQL group by. In SQL, you can't just do a group by, right? In SQL, you have to also use an aggregate function to reduce the groups back into tabular form, right? So relational databases cannot have like groups of things like that, and then you only deal with basically with table form of stuff. But what we did for EF Core 7 to make this very popular kind of query work is basically, as you can see, we translate it to something that doesn't do a group by on the server. So we get back all the rows exactly as they are, but we kind of group them for you on the client side. So notice that there's still an order by there. We order by the key instead of grouping by the key. And then we get basically all the rows for a certain key value, and then all the rows for another key value. And client side, inside EF Core, we pack them into groups for you, into groupings, and give you access to that thing. The key point about group by is, when you think about it, it doesn't actually, just putting a group by doesn't reduce the amount of data in any way. It's just kind of shapes the data differently, right? Instead of getting a lot of rows, you get the exact same rows, but grouped in some way, right?
Yes.
So the same amount of data is basically coming back from the server,
yes.
Which is why we think it's okay to allow you to do group by like this. So there's nothing here in terms of performance that would be bad. You're just reshaping your data, which is why this is fine.
Yes.
But it does not do group by in SQL, right?
Yes.
Which is a little bit weird. So anyway, that was just like
But
a
it's
little.
not inefficient, and it's not bad client evaluation or anything like that. It's all fine. It's just
I like
to
think of it as like two dictionary or two list, right? Those don't really translate to the database, but on the client we can shove it into that shape. Same
yes,
with
exactly.
It's very true. Yeah.
Yeah. Okay. So let's go back to SQL Server, and we can do the same thing on SQL Server, just for completeness. So find all generations. Again, it looks exactly the same, except that we're doing a get level, but this group by in the same way, and it will translate. I'll probably run Postgres. No, I have run SQL Server. Yeah, don't know how I managed that, but that's good. So yeah, so we're doing an order by here in the same way. So translation is the same, Postgres and SQL Server in that respect. Okay, so let's do something maybe more interesting. Should we stop for questions at all, Shai? Or
no, let's go on.
keep
I think
going? Okay.
let's keep going and just show code. And there's more like there's various very legitimate questions of why would I want to use this as opposed to, for example, like foreign key constraints within the same table, like and all that stuff is very important. But I think now we're just looking at what this does.
Okay, let's keep going then. Okay, so I want to find all the descendants. So given Mungo, let's find Mungo. Where's Mungo? Mungo there. So Mungo's got a big load of descendants. So I want to find all of these descendants of Mungo. SQL Server has a function on hierarchy called isDescendantOf. So we can use that to it will tell us, okay, that the hierarchy ID that you're looking at is a descendant of the one that you passed it, or the one, you know what I mean. Anyway, I may have put that backwards when I was talking about it. Interestingly, and I don't know if anyone in chat can confirm this, maybe this is a graph theory thing or something, I don't know, but both Postgres and SQL Server recognize yourself, the thing that you're testing, as being both a descendant and an ancestor of itself. So if I ask for descendant of Mungo, Mungo is considered a descendant of Mungo, which to me was a bit weird. So anyway, I didn't want that in my results, so I just added this other clause, which is like, if you're going to return me, then don't return it. I don't want that one. Okay, so let's just run this so we can see the query. Here we go. So yeah, so descendants of Mungo, and here they are. You can do orderings and stuff to get them in the the appropriate levels and things like that, but I haven't done that right now. In some of the examples in the what's new, I've done some ordering things there. But yeah, basically it's just calling this function is descendant of. Okay, and if we go to Postgres, we have essentially the same thing here. In fact, the method is even called the same, is descendant of, so that looks basically the same. And if I run it, the SQL, looks a bit different when we're doing Postgres and SQL Server, because SQL Server is implemented in the database as a UDT type, and so the methods, look the same. Whereas Postgres, there's more of a translation from methods in the .NET world to kind of functions in Postgres. So we see that here, where in Postgres they actually have this funky operator here, where you're saying this is basically is descendant of. That's what this operator means.
So Postgres loves operators. Everybody who uses Postgres, like the more advanced features, know that there's like a zoo of operators with all kinds of characters, and it's all great fun. But the story behind this is that there used to be, there used to be a limitation in Postgres where if you wanted something to be sped up by an index, what we sometimes call searchable, then it had to be an operator. So you couldn't have a function that could be, it was just, engineered that way. And I heard that went away, that limitation, but that kind of explains every time they wanted to have an operation that could run quickly, like a contains of some sort, then they couldn't introduce a function because they wouldn't be able to speed it up. So they invented some operator, and it's really funny, where you even have operators with 3 characters, right? Because 2 characters aren't enough, so it gets really wild. Anyway.
Okay. So the obvious thing to do next, we've looked at all descendants. Let's find all ancestors. So Longo here is, where's Longo? Longo's there. So all ancestors would be Mungo and Balbo. Postgres, just like it has is descendant of, has is ancestor of. Again, filter out because apparently Longo is an ancestor of himself. Anyway, so yeah, and this will similarly translate to an operator on Postgres, but a slightly different one. Only slightly different. The arrow is pointing the other way, but it all makes sense, obviously. So going back to SQL Server, SQL Server has is descendant of, doesn't have is ancestor of. But that's not really a problem, because if you want to find the descendants, if you want to find the ancestors as opposed to descendants, you just switch the operands around, right? So up here, we were saying where the H1 path is a descendant of, and down here, in order to find ancestors, we're saying where the path of the thing that we're looking for is a descendant of the thing we're passing in. Does that make sense? So all I've done is kind of switch the order of the operands, and now I've got the equivalent of an is ancestor of. And of course, this would work on Postgres as well, but Postgres has, the operator and therefore the method to kind of, do it. So it's perhaps a little clearer on Postgres, but it's not a difference in functionality at all. And if I run this one, then you'll see that we'll get a query translated as appropriately for SQL Server. Okay, there we go. And again, we've got the is descendant of in there. Okay, so things are going to start getting a little bit different between Postgres and SQL Server next. So we've been looking at all the descendants. If we were looking at Mungo, we wanted to, the direct descendant of Mungo is Mongo only has one descendant, so perhaps not the best one. Let's change this to Longo. That would be better. And now I'll find out my query's wrong. Okay, so the direct descent. Oh no, hang on, that's ancestors. Never mind.
Yeah, I
We'll get there
wanted to say
eventually.
something.
We're looking for direct descendants of Mongo. So what we want is these 5, Bungo through Bingo, but we don't want Bilbo, Otho, Boo, or Falco. So there we go. SQL Server has this nice function, get ancestor, which basically says, given this, give me the first ancestor. If it's 2, give me the second level up, third level up. And so we can use this for both finding a direct ancestor, by switching it around like we said before, or finding direct descendants. So I can write a query here in SQL Server that will quite easily find me only things that are the direct descendants of Mongo. So we'll run that just to prove we're not lying. Yes, we don't have to run everything, but it's nice to show the code actually works and look at the query. So there you go. So yeah, so we're doing get ancestor there, and we can see we've got Bungo through Bingo on there. Now, let's look at find direct ancestor in SQL Server first as well, just so we can get that out of the way, because it's basically the same thing, but with, again, the get ancestor call on the other side of it. So in this case, we want to get get ancestor, so we put the get ancestor call on that side of the equation rather than that quite. But the result, and in this case, I guess I already changed it to Bilbo, so we can get all of the ancestors of Bilbo, which should go all the way up to Balbo there. Oh no, direct ancestor. I don't know what I'm talking about. The direct ancestor of Bilbo is, as we know, Bungo. Was it Bungo who built Backend? I can't remember. Bryce? No, you don't remember? Okay,
Sorry.
I think it might have been. Anyway.
These
Okay,
halflings
so
would be very ashamed of your understanding of their family tree.
they would be indeed, yeah. Okay, so let's go and look at this in Postgres. So I'm gonna skip down a bit first, because I've got a way to do it here, and then we've got actually a different way to do it. And the different way to do it looks very similar to the way we were doing it in SQL Server. So, I was talking about Shy. So Postgres has a lot of these things, these methods. Let me actually bring that up real quickly. So on the Postgres documentation here, or let's look in the translations. So Postgres translations, these are the translated functions for the ltree mapping.
I hope everybody can see those funky operators on the right. That's what I was talking about before.
Yeah, so these
Look at that 3-character one, question mark @ greater than. Isn't that great? Isn't that beautiful?
Yes. Anyway, so there's these subtree, subpath, and 2 different subpath methods here that basically go into your, if you think of it as a string representation, and they'll strip off this bit, or they'll strip off that bit, or find the bit in the middle of it. And so you can kind of do manipulations of the position in the tree by manipulating the path in that way. And that's what I've done here, right? So instead of doing get ancestor, I've done subpath, and then take the thing off the end, right? So that gives me my ancestor. And so then this looks basically the same as the SQL Server query did with get ancestor. So let's run that. And we should see something with some funky operator again. Oh no, it's not a funky operator. In this case, it's just a. Oh, sorry.
Oh, you're in debugging.
I'm in debugging.
Yeah.
How did I get?
You chose
output.
Debugging instead of
output. There we go. Okay, yeah. So yeah, it's not a funky operator, right? Oh, is that the? I don't know what I'm doing now. Anyway, am I actually running in the debugger? Is that what's happening?
No, you're okay.
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 Let's run again. I need to get back into where I was. Okay. Okay, so we don't actually have an operator here. It's actually a function subpath, so it looks a bit more simple. But you can see we're passing in 0, -1 there. And this works, bungo, right? My experience of these things, though, these subpath, subtree things, is you have to be very careful because for two reasons. One, because it's easy to get something that matches but is actually matching the wrong thing, especially if your hierarchy IDs are in the 1.2.3. Like remember, I said like you could do a subpath and it gets 1.1 and it finds 1.1, but it was actually because you got the 1.1 off the end instead of the 1.1 off the beginning. So when you run it with another value, it gives you the wrong results. So that I found quite hard to get it right. But it's also an issue. The other issue is they're not very forgiving. So get ancestor is quite forgiving. Oh, am I in SQL Server again here? Is that what? Yeah, because that's get ancestor. Sorry. Postgres. Okay. So, so for example, if I wanted to use this subpath thing as a way to do the same thing that I did on SQL Server, thinking, okay, it's just the same as I used there. So this, subpath is get ancestor. This looks fine to me, right? I mean, it's doing the same thing. It's saying if the ancestor of this thing is that, then then it matches. But what happens when I run this is a big bang. Why is it throwing an exception? Well, the answer is that for some values of H1 path from Patriarch, subpath 0 -1 is not valid. It doesn't return a valid path. And while get ancestor just says, oh, that's fine, there isn't an ancestor, and keeps going. In Postgres, it throws. And this is very data dependent. It depends what you're calling it on. And so it's quite tricky to make sure that you're only doing it when it's safe. So you can obviously do H1 path from Patriarch n level is greater than 0 here, right? And then we won't. And then this should work fine if I've done that right. But you have to be a little careful with these things. Frequently, when I was trying things out, I ended up with it throwing an exception saying you've gone outside the bounds. You've created something that isn't valid there. But now it does work, because now we're never passing the root essentially to this thing, and it's saying the root doesn't have any ancestor. That's invalid. So there are other ways to do this, though. So that's why we have these ones here in Postgres where I'm doing it in a slightly different way. Which is better? I don't know, but this is a different way of doing it. Where I'm just saying, okay, I'm using is ancestor of in this case. So, Postgres has both is ancestor of and is descendant of, but I'm basically filtering the ancestors just to say, if the level, only give me the ones where the level is the ancestor's level -1. And that returns the same, writes a different query, but it returns the same results. I have no idea if one's more efficient than the other or not, or any of that stuff. And even in terms of what's easier to understand, I don't know. Although I find these subpath things pretty hard to. You have to really think about, do I want it from this end, that end? Where's, so this is perhaps easier for me, but it's totally up to you. And anyway, we get the same thing there, and we can do exactly the same trick for finding descendants, direct descendants here, but we're doing n level +1 instead of -1. So it essentially gives you the same kind of thing as doing that, but it's just a little bit maybe simpler or more robust in terms of you don't have to worry about making sure you get a correct path when you manipulate the path. Okay.
Arthur, do you think we should stop and talk about the more conceptual things of or do you want to go on with
very
samples?
soon? Very soon.
Okay.
Yes, but there's one more. I've got one more example. So one of the obviously the burning questions for scholars of Hobbit family trees is who is the common ancestor? Actually, I'm going to change this to the more compelling question. Who is the common ancestor of Frodo and Bilbo? Why did Frodo get back end? Surely it should have gone to Lotho, you would have thought, right? If you're following the normal kind of inheritance stuff, it should have gone to Lotho, right? But it went to Frodo. Okay, now this isn't going to answer this question because we all know that Frodo got back end because Bilbo gave it to him, like in his will, right, or whatever. Although it's interesting, he gave it to him, but then he went off to the west and he didn't potentially ever die. So should it actually have ever been Frodo's? I mean, I don't know. There's a legal question there, but it wouldn't have been Lotho's either way. Anyway, enough of that. We want to find out, who the common ancestor of these two are. So again, there may be different ways to write this. The way I did it is just find the descendants of one, the descendants of others, and where they find all of the ones where those descendants are the Hobbit is both a descendant of Frodo and a descendant of Bilbo, ordering it so we get the closest one, and then print it out. And I just wrote it this way on SQL Server just because that's what came to mind and gave me the right answer for the question that I wanted, which is Bilbo. Postgres, I'd spent a lot of time, and I don't even still know, I talked to Shai about this yesterday, and I still don't know if what I came up with is even the right way of doing things or not, because and maybe Shai can talk a little about this in a minute, but Postgres has this longest common ancestor function that looks like it's perfect for this. And it kind of is, except that it's a static function and you have to pass two things in. So you need to do a query where you're doing a select many to bring both of them back. And in the case, to make it similar to the SQL Server one, I had both the Hobbits queried first and I was just passing them. But in this case, I'm actually, reselecting them in a sense because I couldn't figure out a way how if I'm just passing these in. And then, of course, this thing just brings back the ltree, the hierarchy ID, the ltree of the thing. So you actually have to match it again in order to get back the thing that it matches. And so Shai sent me this simple function yesterday and I'm like, that looks awesome. And then I tried to actually use it. And as always, when somebody gives you an answer and they don't know your actual domain business logic, it didn't actually work for me. So anyway, so this works. We can run this. And
you can also use the SQL Server approach, right? You can also do the same.
Yeah, you could do. You could absolutely do the SQL Server approach, and it will be fine. But anyway, I just bringing this up now because this longest common ancestor looks so useful if you're trying to do these things, but it's perhaps not the easiest thing to use in every case.
So the source of the complexity here is that, like any other function, like in general in SQL, longest common ancestor needs to get two ltrees, right? Like two paths, and it needs them on the same row, right? We're on a relational database, so it's going over like row by row. And then when you want to invoke a function, then you have to get the two values from the same row in principle. Yeah. Now, of course, the thing here, the source of the complexity is here. We actually want two ltrees from different rows, right? Yeah. We have various rows, and so this is why when you look at the actual SQL, the select many translates to a cross join. This is basically a trick of ours to take two rows and to flip them around horizontally so that you can take those two ltrees, which were first vertical, and make them horizontal so that we can invoke that function. Here, I think, I mean, definitely compared to what I experimented with yesterday, there's more complexity than what I tried yesterday. But the basic principle of it is the same. So we're using select many, which is basically a way to so this is a self join, right? This is we're joining the table with itself, and then theoretically all the combinations of different hobbits are joined together so that they're on the same row, so that we can call longest common ancestor on them. which is a nice trick. It's not just an ltree trick. It's something that's used in SQL programming in general, just so that people are aware.
Indeed, yes. It also, I was going to try and find what you sent me yesterday, but I won't. But it also sometimes looks easier to do a select many using the comprehension syntax rather than doing a select many where you can do a join and a join, right? And then it looks easier. Anyway, this is the end of the kind of common examples between SQL Server and Postgres. We can answer some general questions, and then we can also go and look at some things that you can do with Postgres that are conceptually a little bit different from what SQL Server supports.
Right. So I want to say a few things. I mean, I think there's a discussion to be had. We had this discussion offline, but I'll show as an introduction to this. This question has come up at least 3 times, I think, in the chat. I'll highlight one of them. So the question is to compare hierarchy IDs or ltrees with just the plain old style kind of child-parent relationships with int-based identity and foreign keys. So just I'll show another one who basically that asks the same question. What about, ID parent ID using recursive CTEs for all that kind of stuff. So first I want to clarify what this means, right, for people who are not necessarily aware. Instead of all this buzz around ltree and hierarchy ID, if you just have your basic relational database, the way to represent to model this is very simple. Every row can have a parent ID, which is just a foreign key relationship to the same table. So basically, you have a person in that or a halfling in a row, and then each halfling has a column that says, who is my ancestor, basically. And using that, you can see how you can basically model. It's the same thing. You're modeling a tree. You're organizing all the rows in the table into a tree by simply having a single column which has a foreign key constraint back to that same table, right? And that's a very, very common way to model things around. And indeed, it is an alternative way to do exactly what Arthur has been showing you, which is having a table of halflings. Now, at this point, I want to go into. Of course, this begs the question of, so why are we doing it this way with hierarchy ID, right? So first, I came from the Postgres world with ltree, right? And if you look at how people use ltree in general, you look at the samples, you'll see something a little bit different from what Arthur showed. So in Arthur's example here, the things inside the the hierarchy ID or the ltree are rows in the table itself. So it's a hierarchy that basically is applied to the row of the tables, right? So inside the ltree for a given halfling, you have other halflings. And this, by the way, is why you have numbers in there. Those numbers actually correspond to the primary key, right, of those other halflings, right? So we're basically is that not correct, Arthur? I see you're shaking
They don't
your head.
have to respond to the primary key, but they are, in a sense, an alternate key if you don't, in some sense.
They identify
yes.
the other rows in some
way.
They
identify the position of that row in the hierarchy. Yes.
Exactly. And notably, what this means is if we want to suddenly, do some sort of reparenting or change in the hierarchy, that actually would require quite a bit of potentially complex queries, right? We'd have to go over all the hierarchy IDs and of everybody in the database in order to modify, some number in the middle to some other number in the middle, right? Like just to make sure that people understand what it means when my hierarchy ID value is actually referencing rows, right? So just the alternative, what I've been seeing none of us here are experts in hierarchy database things, but the thing I'm used to seeing is a little bit different. In Postgres, like the first sample that you see is not something that refers to other rows, but just something that applies a classification or an organization to that specific row. For example, let's say you have your employees, right? So you have a lot of employees, and you want to say which departments these employees belong to. So departments are not employees. This is the crucial point here. A department is not another row in the same table that we were just discussing. Departments can be hierarchical. So you might have, the engineering department that's part of the R&D department, that's part of this department. It could be arbitrarily deep. So it is a hierarchy. But the things inside the ltree generally don't represent at all other rows in any way, right? The rows are, you could think about them as the leaves, the employees or whatever, but the thing that you shove inside your ltree, your actual ltree value, is not at all other employees or other things in other rows. This is why in the ltree sample, maybe Arthur, we can show that sample with I can also do this.
Yeah, I can. I'm going to show
just
the
to show an
example.
alternative thing.
Yeah.
Like from the docs.
Okay. Let me do this. Okay. So here's an example.
Great. Right. So this is the example I'm used to also working with. I wrote the tests using like for the Postgres provider. I wrote all the support for ltree, and I use these tests as well. So what you see here is a sort of categorization of subjects, right? Or whatever. There's top, which is an artificial node. That's the top, the root. And then there's science versus hobbies versus collections. And under that, there's astronomy versus amateurs versus pictures. The crucial point. Sorry, go ahead.
No, I looked at this. I'm like, what is this? Is this really subjects, like collections, like it's just things, interests, maybe? I don't know. Anyway, keep going.
Maybe it's some sort of classification that makes sense for you for your rows in your table. That basically is what ltree is supposed to be about, and that's also why it's about labels. This really is just a form of labeling that also happens to support hierarchies, trees, right? That's all that it is, which I think maybe is philosophically a little bit different from the hierarchy ID approach. Maybe I don't know this again. We just discussed this, Arthur and me, a little bit in the past few days, but none of us are experts in this in any way, right? But the point I'm trying to make is if you're using this kind of organizational structure in ltree, then obviously it doesn't make any more sense to compare it to the traditional parent ID kind of thing, because the relationship is no longer between rows. So you can't just shove a parent ID and point to another row, because the ltree doesn't contain rows anymore. It contains some arbitrary thing with strings, basically. So I guess now we can go back to the original question that people have said. If we want to compare this with the traditional thing, then that means already that we're using hierarchy ID in a way that represents a tree over our rows, right? And where the rows themselves participate in the tree. So it's the first model rather than the second model, and that's a point that I wanted to drive home, right? I talked for a long time. Arthur, does this make sense? Do you want to add anything?
I can talk too.
Absolutely.
So yeah, I think that makes sense for the Postgres view of it. But I mean, the SQL Server one is called hierarchy ID, and in most of the sample databases, it truly is the primary key. And if you think about it, it's the difference between knowing your manager or your management chain, right?
Right.
So if you meet another employee in the hall and all you know is your manager, and you want to know who's our common ancestor, effectively, you'll have to go find your manager. He'll have to go find his manager. They'll have to find their managers. But if you know your chain, you can answer that question with only two pieces of information. And that's why these are more performant and more optimized, because any two nodes can kind of know their relationship to each other without having to write a CTE or all these joins, to try and figure out this information.
Right.
I think that is critical. And if you read the SQL Server docs that I have a little bit at least, being able to do these kinds of queries efficiently. So I can find all the descendants efficiently, and do that without a recursive CTE that in its name has to recurse, right? You don't need to do that, right? Because you've got all of that stuff encoded already in the hierarchy ID. That's a big reason, I think.
Exactly.
I'd love to know why they added it to SQL Server, like what the use case was. It makes pure speculation on my part. I have no knowledge on this, but it makes me think when they were doing like WinFS and they were going to store file systems and stuff in the database, that they were like, we need an efficient way to be able to query file systems and things in the database, because that's really one of the big advantages of it. So
I think both of you obviously hit the nail on the head, right? The point is that you can you have all the information right there on the row, basically, and you have indexes. That's basically all. I think that is enough, at least for me as a perf guy. That's enough of an answer for sure, right? It's a beautiful feature just just looking at that, right? So I'm sure we've been throwing this term around, recursive CTEs. I'm sure people here, our viewers, aren't necessarily aware of it. I don't think we have an example like offhand to show, but there's a thing in SQL called a with clause. Or a CTE. That's a common table expression. That's what CTE means, and it's a way where you can basically it's the only way where you can introduce recursiveness into SQL in general. SQL does not support recursiveness except via this tool, which is called recursive CTEs. And when you use the parent ID, the classical way to model a hierarchy, then this, if you want to do something like get me all the descendants of somebody, then you can't just write a select to do it, because you'll only get, if you ask, get me the descendants of X, then you'll only get the direct descendants, right? If you want to go and get those descendants as well, and then those descendants as well, then that is a recursive query. And this is a thing that you can do with this tool called recursive CTEs. However, that every time is like yet another big query that you're doing in a recursive way, right? So efficiency-wise, this is not ideal. Recursive CTEs.
It's like doing lots of joins to get the.
You can look at it that way. Yeah, exactly. I mean, there might be tricks and various ways to optimize it in the database, but it's not going to be like looking at a specific row and then, and basically, or just looking at all the rows whose hierarchy ID begins with something, which is a pretty simple thing if you have an index. And SQL Server supports, I looked into this a little bit, it supports indexes over this, which allow you exactly this kind of query. Give me all the rows where the hierarchy ID happens to start with 1/2/4 or whatever.
Yeah.
Okay. On the Postgres side, you have the same thing. So you have efficient indexes as well on the ltree, but things don't necessarily, as Bryce said, things don't correspond to rows. It's like a different thing. It's an arbitrary classification thing that's detached from your rows. Basically, it's just a bunch of string labels, right?
The thing
and
is,
by the way, sorry, I'll just say one last thing. And if I'm not mistaken, and Bryce will correct me on this, one of the major differences here, people have been asking, can we have an abstraction over these two things? Like one big difference, for example, in Postgres, the labels are just labels. They can be textual, as you saw in the example. Whereas, if I understand correctly, that's not the case in the SQL Server, right?
Like spatial, there's sort of the standard, right? There's a spatial standard, and all the databases implement. There is no hierarchy ID standard.
Exactly.
They kind of invent their own solution to these problems.
Exactly. Yeah.
I mean, I think from an abstraction, so that ties in what I was going to say, which is that Postgres supports the kind of more restricted view that SQL Server has over these things, but Postgres, being the overachiever in the database world, can go and do other stuff that is conceptually somewhat different from what the SQL Server thing does. So in terms of abstractions, I think you could imagine an abstraction over the basic concept of them as IDs, and that could be implemented in both, but it would be limited to to that. And then I have no idea what MySQL or any other database support in this. The one thing that Diego brought up years ago was, it would be really cool if we could actually map these things to navigation properties. So like I've got a halfling, and then its ancestor is a navigation property, and then it has a collection of its descendants, right? And so in my object model, I have something that looks very nicely like a C# object model, but then that translates to hierarchy IDs or ltrees in the databases. And I think that would be really cool. I think it's non-trivial to do in some respects, but I haven't tried to do it either. But I think that would be a very interesting specific abstraction of this that would fit to both of them and kind of allow you to model these things in perhaps a more natural way.
And that, I think, actually goes back to this question of the parent ID that people were asking. In effect, the ltree, the hierarchy ID rather, value that you have there is kind of like a foreign key, right?
It is, yeah.
Your parent and also all of their parents, right?
It's
all the way up the chain.
It's a key that contains everything, all of its like primary
like a
keys
list,
in it,
like a variable length list of foreign keys, you could think, right?
Exactly. Yeah.
We could. You could think about like something like that. Yeah.
We're going to look at some kind of cool Postgres examples that think about it in this other way in a minute. Before we do that, though, I just want to go back to something that Shai said, which is about manipulating these things. So one of the reasons why I didn't make it, and I was going to try and do this on Postgres, but Postgres, as far as I can tell, doesn't. You could write this on Postgres. You could do this because this is client-side stuff, but I didn't have time to do it, so I haven't got the Postgres example of this. But this is on the .NET blog, which I copied and pasted from what's new in EF Core 8. So either place has this. But the idea here is I actually do want to take a subtree. So if we go back, if I can find my thing. So what did we say? Let me read the text on here first. So Shai reckoning 1752 Longo gate, we revealed that Longo is not in fact the son of Mungo, but actually the son of Ponto. So obviously,
news.
Yeah, I know. So Longo here, not the son of, was that who it was? I've forgotten now. Longo, not the son of Mungo, actually the son of Ponto. Okay. So we want to move Longo, so this tree, all of Longo's things, and put them under Ponto here, right? So this is a place where ideally we don't want the primary keys of Longo, Otho, and Lotho to change because they're actually the same entities, but their place in this tree structure has changed. So it's we use the word reparenting in databases or object models a lot, but this literally is like I'm reparenting Longo from Mungo onto Ponto. And SQL Server has this fairly useful function for doing that called get reparented value, where you basically say, okay, given this descendant, go from Mungo to Ponto instead. And so you can load the descendants into EF Core, run this. This is a client-side thing. I mean, it probably translates to server. You could do with an execute update or whatever as well. But in this case, I'm doing it on the client side. And then save it, and then it's going to then send back. And you can see actually here, it's interesting to see the parameters being sent in the compact binary format.
Nice.
Yeah, and then after that, now if we do Mungo, we get these things. Well, Ponto now has Longo under Ponto. So there is actually a case where you can separate this thing out from the primary key and say, actually, this is not necessarily the primary key of the thing. It represents their key within the tree, but that could be conceptually different, and we might want to manipulate that to move parts of the tree around. So file system, for example, copy this folder to here, right? Now, maybe you would want to do that by deleting it here and recreating it here, and I don't know. But either way, it's conceptually you're moving things around in the tree without changing their primary identity, as it were. Anyway, so that's just an interesting thing there. And then, so let's go. So because Postgres has this kind of representation of it, and we're not thinking of it in strictly in terms of keys in a tree, in a sense, key like on the SQL Server model, we can do some interesting things with it. And I'm not going to show very many of them, primarily because I ran out of time preparing the demo. But I am going to show some pattern matching and free text search that you can do within these things, which is kind of cool. So so I have in here, I've called these things interests because, like I was saying to Shai, I don't know what these things really are. They don't map very well to an entity type in this conceptual model like we were talking about. I put ltree as the primary key in an interest. I mean, all we really care about is the labeled tree, the labels in the tree, So I put comments on here like, okay, I store some comments about each of these things. But again, it's like, does this really map to an entity type in the same way that it does for the other case? I'm not sure. And then for the Cedar, I have this case where now we're doing the same thing, excuse me, but we're just using the labels. Shai's lights have turned off. These labels from the Postgres example. Okay, so let me go to the Postgres example here, and I'm going to change this to interests, contexts. Go, and then comment out this stuff. Okay, so I've got a pattern matching example here. So what we can do here is we can actually say we've got this matches query method, which is going to translate into one of those funky operators, and it's going to match star.astronomy.star. So basically return everything in here that has astronomy. I'm going to run this, but let's go back and look here. So this is interesting, you'll notice, because astronomy actually appears at 2 different levels in the tree. So rather than just being a number, we're actually saying there's semantic meaning to the fact that the word astronomy appears here and appears here. They are related in a way that isn't true if this were just 1, 2, 3 and this was 1, 2, 3, 4, right? Then you wouldn't, just because this is 1 and this is 1 doesn't mean they're related. But the fact that this is astronomy and this is astronomy and these are, we're saying there's some semantic meaning to that. And we can, there we go. And we can now, run this query, which uses what's the operator it uses? Parameters. Oh, it's this one. It's just the tilde operator. There you go. And so there we can get back everything with astronomy, no matter what level it's at. So it's basically, doing pattern matching. And of course, we could do some fancy patterns. I don't even know what this pattern means, but maybe one of Bryce or Shai knows what star.bang pictures at astronomy means.
I don't know. It's a whole query language in there, which I don't know.
Yeah. So in this case, we've got, I guess it's not returning. Yeah, I don't know. Anyway, it's matching. Let's assume that that's a correct match for that pattern. Otherwise, Shai has a bug, or Postgres has a bug, probably more likely. Okay, very similar to that, we can do a full text search on these things. So in this case, matches, instead of here for doing the pattern matching, we're doing matches L query. In this case, we're doing matches L text query. So we can run this again, and it will use a slightly different operator. So yeah, so it's using the at operator here, but it's bringing back. I don't know anyway, because I did this like in 5 minutes before the show. But it's presumably doing a free text search on the in the ltree text. So basically, there's a bunch of other things here. So 2 pages. We stopped doing show links, haven't we? We need to do those again. So if we had show links, these would be going in the show links. 2 documentation pages. There's this documentation page for the Postgres support, which talks about all of these different things, goes through, conceptually the difference between the text query and the L query for the free text and whatnot, and then talks about all of the different operators here that you have. And then the functions. So we mentioned subtree and subpath and n level. You can also do an index and then some other stuff here. And then it talks about creating indexes on here, which is useful. And then it has some of these examples where I just copied and pasted and put them into EF. And then on the NPG-SQL EF core provider page, there's the functions of ltree and what they translate. So you can you say, okay, so I've read that, and I know I need the question mark at greater than operator. Okay, then I'm going to pass a list of ltrees and do first or default and do is ancestor of, and that's what it'll translate to. So Postgres has a lot of stuff there. But in general, I think we've covered why you probably might want to use these things, how you can do it in SQL Server and Postgres, and at least hopefully giving people an idea. So any questions that we should cover before we end, Shai?
So there's one that I want to speak to quickly. So what is the benefit of using this approach versus JSON-B? So basically storing a JSON
Interesting.
document. So first of all, what we've been talking about here, both ltree and hierarchy IDs are a path within a tree, right? They are a specific path, whereas a JSON document represents an entire tree. That means that every row has a whole tree there. So JSON is just a different thing. If you're trying to model a hierarchy where each row is part of that hierarchy, I don't think JSON-B makes a lot of sense. Of course, if you don't, for example, if I were in some other database like MySQL, which doesn't have one of these, then one way to do this would be to store an array of, all the IDs of my parents or all my categories or department names. And since databases generally don't support arrays, you could use JSON to hold an array on each one of your rows. But that's not like a full-fledged JSON document. It's just a way of holding an array. So it's important to understand that conceptually these are arrays of IDs or department names or whatever it is that you want. They're not a tree. They make up a tree. If you take all of your rows together and you put all of them together, then you have this big tree, but each row on its own does not contain a tree. It just contains a path within that tree. So that was my answer around this. And the last question for you, Arthur, is, will the sample code be available?
Yes, I will. I'll put it up on my GitHub account, AJC Vickers. I'll push it up there. If not tonight, then tomorrow. So, yep, I will definitely do that. And also, you can also look in the what's new in EF Core. So, aka ms/ef8-new. And that has a bunch of the SQL Server stuff there with runnable samples that you can get right now, where we call hobbits halflings, but it's the same stuff. But yeah, I'll put the Postgres stuff up as well.
So, I mean, it's nice. I mean, the samples are great because they're EF code using these two APIs, but in general, you can just look at the docs, understand what it is that you want to do, and then just call the methods in our docs, which translate to those operations. It shouldn't be too hard to piece together, but of course, samples are always even better.
I see somebody asking about MySQL there. I don't know if it's been asked before. So I have no idea whether there is support for this in MySQL or not. But likewise for SQLite, Bryce, I don't know if SQLite has anything like this. But both the MySQL provider and the SQLite provider are open source. And even if you don't add it to the provider, you could probably create a package in the same way the community did for that. And so feel free to go in and look at it or whatever. It's not something that we on the team are planning to do, but we'd be happy to help out with the community advice, make sure it works the same way and all that kind of stuff. So, yeah. Okay.
Cool.
I think that's it.
Yeah, we're even not like super over time, only like
Only
17 minutes after the hour.
I know, it's the record for us.
It really is.
Okay, thanks everybody. Appreciate you watching, and we'll figure out something to do in 2 weeks' time. Probably the day before. Okay, thanks all. Bye.
Bye.